This is Lab 9 with Alex Floor doing Physics 1 MO5. We will be observing and tracking the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. While this motion appears more complicated, we will find that we can understand and predict this motion. To do this, we will be using Newton's second law, or the momentum principle, and the first law of thermodynamics. So we use the video of Professor Greco dropping the spring, and we tracked the points of it. We calibrated the video using the distance from the origin to the spring, which is 0.7 meters. And the different time frames for this video are 1 over 10.5. So as you can see here, we tracked each of the oscillations of the spring at each time interval. And we save these numbers, the data that we recorded over here, and put them into Excel to be used for our Python models. So as you can see in Python here, we are going to be comparing the simulation to the actual video that we have. So we start with we put the initial conditions in, as I said before. The mass of the video is 0.42 kilograms. And we start with the initial position, which is the first point of data that we collected from the video. And we have the different values, the Ks and the L naught, which were found in the in-class lab. So using all the calculations that we did there, we are going to plot it in a graph, and we're going to be comparing the ball's position, x position, to the ball 2's x position. So when we run this model, we see that it's a fairly good fit, and the simulated model and the one from Tracker are actually very close together, and the graphs oscillate very similarly. So the next thing we're going to do is, we found the x position, we're going to next find the y position. So we just have to change these points here, and we will run the model again. So as you can see, the physics of this is still the same and the data looks good. However, the graph is changing, but again, the oscillations are fairly similar to each other. So the next thing that we're going to tackle is the what if questions, and there's actually 3 parts of those. So you can see it's still oscillating. So we're just going to see what the model means. And the green model is the tracker info, and the blue ball is the weight from the tracker video. The red model is the simulation, and the orange ball is the simulated mass. So we're going to compare these and see what information. And again, here is just the information that we had. Next, so we're going to start here and compare what does this mean. So the first question says, compare the period of oscillation you found from examining the x component of the position with the period of the oscillation determined from the y component of positions. Do they differ, and if they do, can you explain why? So as you can see here, this is the y oscillation and this is the x oscillation. I'm sorry, they're actually backwards. This is the x oscillation and this is the y oscillation. And as you can see, they're both fairly similar to each other, the oscillations of each one. And we just found that by measuring from trough to trough. And they differ because the initial energies are different that are inputted into the x and into the y. The second what if question says, with your new choice of systems, determine the work done by the surroundings. Is the energy principle satisfied? And the energy principle is satisfied, and when it's incorporated, the ball, earth, and spring as the surroundings, the surroundings actually have a negligible effect, which means there's no work done, and therefore there's no energy change in the system, so the energy principle is satisfied. The final question says, when determining the gravitational potential energy in your computer model, you made a choice for the location of the origin. Change the location of the origin in your computer model so that y equals 0 is the location of the mass when it's at rest in static equilibrium. This corresponds with the location, distance, L naught plus mgk, below the attached point of the spring. How does this change the location of the origin, change the physics of the system? just because the physics of the system changes doesn't actually mean that anything else in this, just because the position changes doesn't mean the physics of the system is going to change. So we know that the physics of the system won't change, and so the changes in the energy states stays the same because the object behaves the same. This was Lab 9. Alex Floor, thank you very much.